Good morning, everyone. This is we come back to the third day of our summer school. Today we are going to have two speakers, Professor Xiaodong Xu and Professor Vanishing, talk about 2D. So Professor Xu will talk about the 2D magnets and heterostructure. Thank you.
Okay, I think it works, right? So today I'm gonna about two lectures and on 2D magnets and heterostructures. So as any, if you watch a movie online or YouTube or Netflix, anything, right? The first thing you saw is actually commercials, right? So here's my commercial. And in case you haven't been to Seattle, actually it's a really beautiful place. Here's the picture I took near, there's a park, it's a gaswork park near the campus. And it's gorgeous view. We can take pictures. This the skyline of the cities, and we have Space Needles, right? There's a football stadium just near here. We used to be a champion, not anymore. And well, Seattle always famous for coffee. This is actually the first Starbucks in downtown. I mean, in the whole world. So, and we also have a lot of risk. In case you're into these, right? You know what I mean. Here's the campus. We have this took a few years ago, but we have these lecture halls. We have office labs, and we have these peanut shape. Nobody knows what it is, but I call it p-orbital. All right, and you well know, right? My department, we have these brilliant theorists, David Solis, and unfortunately passed away this year. But he built on Solis' legacy. We have these. We originally just started these Solis Institute for Quantum Matter, so TIQM. Actually, the kickoff will be next January, and we're going to have fellowships or visitor programs, and well. You guys are welcome to come. And here's a real commercial. The real commercial is we actually, in the last few years and in the near future, the condensed matter program, especially in the quantum material, grow rapidly. So here's the main experimental for the first row, and the second row is the theorist. And we cover a broad range of topics in the quantum materials, right, from superconductivities, magnets, topological materials, strong correlations, anything which is interesting. So, and as far as I know, all the PS are looking for postdocs. If you're interested, I'm sure we have a lot of candidates here, and please feel free to drop us an email. All right, I'm done. Any questions? Actually, I'm not finished. So we also have in the last couple of years, right? There's a huge effort in terms of quantum computing, and the Seattle is a great place. Everybody, probably you guys don't know, Microsoft actually putting a lot of resources in developing these topological quantum computing. And I just met Leo Hohen, for example, a couple of days ago. He comes to Seattle every 2 months, the same as Charlie Marcus. So we also build these quantum X in the campus, and in addition to that, we have We have actually several quantum material centers. For example, this one is the MEMC, which is the NSF supported MOSAC center. ProQM is a ERFIC center supported by DOE. It's a joint effort between Columbia, University of Washington, and also Carnegie Mellon universities. And the last one is called Northwest Impact. It's a joint effort between University of Washington and also Pacific Northwest National Lab. So we have a lot of things going on. It's a great place right now. All right, so today I'm going to talk about 2D materials, and you've probably heard a lot already, right, for this week. I'm going to quickly go through these, right? 2D material has a broad range of physical properties, from graphene into semi-metal. We can have semiconductors, superconductors, well, ferroelectrics, for example, and quantum spin Hall insulators. You probably heard yesterday already, right? And so starting from several years ago, when I look at all these material systems, and what I realized is there's something was missing, was two-dimensional magnets. It's not only important, right? It's not only important for basically to kind of complete the toolbox of 2D material, but I think there's actually potential real applications we can do, for all these data storage, for data centers, for cloud computing, etc. From fundamental physics point of view, we all know that this magnetism being studied for a long time. Why we want to go two-dimensional? And my motivation is, as any three-dimensional solid-state systems, right? The basic material properties, such as the thermal surface, crystal symmetries are given. But for condensed matter, if we want to understand the electronic phases or control the phase transition between different electronic phases, what we would like to do is actually want to control the phase property in situ, right? To tune one phase to the other, for example, or just control the thermal levels, control the crystal symmetries, for examples. These can be done in a bulk crystal, but it's challenging, right? So what we know is for the two-dimensional system, actually, it's an atomic thing. So what it means is, well, it's easy to apply electrostatic gatings to the system and can drastically dope the system and induce, for example, phase transitions. Or we can just apply electric fields to the system and change the fundamental properties. We can also do heterostructure engineering. We all know, right? Scotch tape is a powerful technique, even though it's very simple. And because of van der Waals forces, and we can stack any 2D material on top any 2D materials. So these give us a lot of freedom and flexibilities to engineer artificial quantum structures. And I think we're only limited by imaginations. So the last one is the control we can apply, right? Not only just by electric field, by interface effects. You all know, right? There's trace angle control can create new electronic states, and we can also apply strengths because anything any materials, when you think down to a two-dimensional, you can apply large strain to it, right? Just like silicon, for example. If you can make a monolayer silicon, actually you can apply large strain to it. So this is the advantage you can get with 2D. And the other very powerful technique we're trying right now is pressures. So we know pressure actually is a useful technique to, for example, to get the high temperature superconductivity, right? But for 2D materials, it's a van der Waals structures. So interlayer coupling actually is critical. And then the pressure actually is a very useful technique to control this interlayer coupling, right? For example, by control the interlayer separations or just control the layer stacking arrangement. Okay, so I'm gonna show you an example today. All right, so here's an outline of my lectures. Actually, I think I may be a little bit ambitious, but we'll see how far we can go. So in the first part, I'm going to talk about the fundamental property of these particular magnets, which is chromium and triiodide. I'm going to show you the fundamental property of these. And then at the end, I'm going to show you our new progress in terms of understanding how the stacking arrangement is going to change these magnetic properties. And the second part, I'm going to focus a little bit more on heterostructures, but initially I will talk about our recent work on electric control of 2D magnetisms. Then I'll show you a very exciting example, actually. Personally, I'm pretty excited about it, is these new effects of spin lattice couplings in these 2D magnets. Then the last part, I'm going to show you how we can use proximity effect to control the spins, pseudo-spins, or even topological edge states in quantum spin Hall insulators. All right. So, like I say, the 2D magnets, or magnetism itself, has been studied for many, many years. But if you look into the literature, you will find actually there was no monolayer semiconductor or insulator with intrinsic magnetisms. The close example is called diluted magnetic semiconductors. But just as the name indicates, right, for these diluted magnetic semiconductor, the spin density is low in the system. Therefore, will limit the fundamental physics you can study because of these low spin densities. The second is, well, monolayer metals actually with intrinsic magnetism indeed exist. For example, like monolayer cobalt on copper and monolayer nickel on copper. But the substrate is copper is quite important actually. Therefore, the isolated 2D magnets actually did not exist. The challenge of what I see is in the past when you go to when you try to get these two-dimensional magnets, they usually use a sputtering or use MBEs, right? So those are kind of a challenging technique to go really thin because, for example, use MBE. You can go to monolayer, but you cannot grow any monolayer on any materials. The substrate is really important. So epitaxial matching, right, is really important. But we all know now we can go 2D materials. For van der Waals crystals, if you can find any van der Waals magnets, and if you're lucky, they can exfoliate into monolayer, then there's a chance we can get 2D magnets. Okay, not every van der Waals crystal can be exfoliated. Okay, so you have to be very lucky. And so when we started this project, we kind of focus on these halide systems. There's many of them, as you see here, right? There's a list of them. They have a very different magnet orders. And the challenge is to find out which one is a good one. For example, as a student, right? If you started with a crystal and you try to exfoliate, it doesn't work. They will tell your advisor, okay, it doesn't work. And you very quickly, you may lose your passion on it, right? That's the truth. So luck is very important. And turns out we're very lucky. We started with this chromium trilide. And we started from this because we don't have a choice. My collaborator only have this crystal. Either you try it or don't try it, right? So okay, I told my student, then let's try this chromium trilide. The nice thing is the student asked to do it. He was a first-year graduate student, so he's highly motivated. What I told him is nobody has seen 2D magnets before. If you did it, you're going to be famous. What I didn't tell him is if you failed, actually, I'm going to add another year in your graduate school. But well, he's a lucky guy. So initially, when we also work with Pablo's group, actually tried to get these monolayers. Because these monolayers, these 2D magnets, they are easily exfoliated, but they're also not stable in the ambient conditions. So we work all these in a glass box, and here I just show you optical microscope image of the samples. Right? Just by optical contrast, you can already see 1 layer, 2 layers, 3 layers, etc. So it's quite easy to exfoliate. The only challenge is it's just not stable in the ambient conditions. And my collaborator, Michael McGuire, actually, he initially, when he told me, about these chromium trilide, what got me really interested is he showed from his from his screen measurements, he showed this particular crystal has very strong outplane anisotropies. So this is very important because we all know as you think down the crystals, right? There's a Merman-Wigner theory. It says if the exchange interaction, Heisenberg exchange interaction is anisotropic, then there's no long-range order in a 2D or lower dimensional limit, right? But so we need anisotropies. And what he showed is there's very strong outplane anisotropies with lower spin point outer planes. This is good news, right? The second thing, what he told me is the Curie temperature actually quite high for the bulk crystal. It's 60 Kelvin. This is also important because, as we know, when you thin down, the Curie temperature may drop. But there's a lot of room below 60 Kelvin, right? So both promising signatures. So we started on these, like I said, we exfoliated, and we built these Magneto optical Kerr rotation measurements. And it's quite a simple technique. The essence is you shine linearly polarized light to the samples, and you look at the polarization rotation in the reflected light. So this angle is called Kerr rotation angles. And the Kerr rotation angle is kind of a hallmark of time reversal symmetry breaking in the systems. Well, the subtlety is if you just see the rotation of the light, doesn't mean you have a Kerr rotation, okay? Because there could be artifacts in the system give you a little bit of rotation of the angle. So the real measurements you should do is you measure Kerr rotation, but as functional magnetic field, as I show here. So there's 2 curves here, right? One is the magnetic field scan up, the other is magnetic field scan down. So if you measure the Kerr rotation as functional magnetic field, it's called MOKE. If you see a hysteresis, that tells you you do have a ferromagnetism in the system. Okay, that's important. So from now on, right? If you see a hysteresis, you know there's ferromagnetism. That's the main technique we're going to use. So the measurement down here is in a bulk crystal. Then we just go directly to the monolayer. And what I show you here is the co-rotation intensity map without applying magnetic field. And the temperature is 15 Kelvin. Basically, we just cool down the sample and doing nothing else. Then what I show you here is a map, right? You already see there's homogeneous co-rotation signals across the sample. Indicates we do have a ferromagnetism in this monolayer. But as I just mentioned to you, see Kerr rotation signal doesn't mean we do have it. So we can park the laser at one spot in the sample, then I scan the magnetic field, and then we see this hysteresis curve. So this does prove we do have a ferromagnet with out-of-plane spins. So these are actually it's icing ferromagnet for these particular examples. We can also measure the remnant magnet co-rotation signals as function of temperature. So these give us the measurement of Curie temperature in the monolayer. Actually, it's 45 Kelvin, not too far from the bulk crystal, right? It's about 60 Kelvins. So this just shows for this monolayer, ferromagnet has pretty strong out-of-plane magnetic anisotropies. And what's really interesting in the system is we have these layer-dependent magnetic properties. For example, in the monolayer, right, I have these, you already see this co-rotation, there's a hysteresis. When you go to bilayer, the hysteresis vanishes, the co-rotation signal also vanishes at the small fields. And if you go to trilayer, the signal comes back. So initially, we kind of puzzled by these for a long time. Then we realize it's caused by these layer, kind of a layer interlayer coupling. It's anti-ferromagnetic. So what that means is, first of all, when the magnetic field is large, right, you can align all the spins in one direction. So we get the magnetizations, then we see large co-rotation signals. However, when you're at the small magnetic field, for individual monolayer, it is still ferromagnetic, but interlayer coupling now becomes anti-ferromagnetic. So the magnetization actually is compensated, right? Therefore, there's no net magnetizations. So there's two ground states. They're time reversal of each other. Then we can extend this concept in the trilayer, so we can understand why trilayer there's actually a hysteresis curve, right? So for the trilayer, if we, based on bilayer, we know the interlayer coupling is anti-ferromagnetic. Then in the trilayer, we should have a structure like this, right? You know, for example, the top layer is spin pointing up, in the middle pointing down, and the bottom pointing up. So we have a up, down, up configuration. If we consider the magnetization for individual monolayer as a unit, which is 1, then you will know, right, the magnetization, total magnetization for this particular state should be 2 minus 1, should be just 1, right? Then there should be another state which is time reversal of these. Then the net magnetization will be minus 1. Okay? Then without any calculation, you know the co-rotation signal from the top state to the bottom state, the ratio should be around 1, right? That's exactly what we see. Okay? Then you can convince yourself. If you apply magnetic field to align all the spin in the same directions, now you count it, the total magnetization should be 3, right? Then the ratio of the co-rotation signal to these ground states should be 3 to 1. So that's also what we see. Okay? So this actually kind of a very simple, but just easy to understand what is magnetic states by just measure the co-rotation signal. Okay? So the same thing we can get the other one is around -3. So each step whether you show here is a spin flip transition. Basically, one layer flip its magnetizations. So we can also understand the same feature for the 4 layers, right? The ground state is up, down, with net magnetization close to 0. And then once we apply magnetic field, and then 1 layer flipped, okay? Therefore, there will be 3 layers pointing up and 1 layer pointing down. But the complexity coming from this minority layer with spin pointing down. This minority layer can be anywhere in the system, right? So there's 4 positions for it. But they corresponding to the same magnetization M equal 2. So by these co-rotation measurements, actually I cannot tell what is the ground state of this one. Later on, I'm going to show you how we can distinguish these, okay? And the last one is you apply the field and you get net magnetization 4. Then you can see the signal from these states, right, to the intermediate state should be 2 to 1. So that's about what we see, okay? The top is 14, the middle level is 7. So everything works well. So the short summary is, for monolayer chromium trilayer is an intrinsic ferromagnet And for atomic thin chromium triode, actually it's a layer anti-ferromagnetic. The interlayer coupling is anti-ferromagnetic. So the next question I want to address is what's the insulator property of the resistance? So I'm going to talk about the spin polarized, the ligand field, the photoluminescence on the system. And first of all, I want to say is before, I looked into literature about what the chromium triode is actually. When we started, there are only 5 papers from 1960 something to now, right? Only 5 papers on, actually less than 5. And if I look into the literature, there's no single report on any of the, photoluminescence from these magnetic insulators with intrinsic magnetism. So for any for any van der Waals crystal, if you see them down, there's no guarantee you're going to see luminescence, right? So we can also lucky here. So the basic idea is very simple. What I told my students is, well, if it's an insulator, there will be a gap, and you shine light to it, you should see luminescence. But this is not the truth, actually. I will tell you why. And we also got lucky here. So the measurement we did is we shine linearly polarized light to a sample. So linear polarization, right, is a superposition with the sigma plus and sigma minus. Doesn't break time reversal symmetries of the system. Then we measure we do this circular polarization resolve the PO measurements. If the system doesn't break time reversal symmetries, then there should be no preference to right or left circular, right? But if you see a spontaneous circular polarization, it will mean the system actually has time reversal symmetry breaking. So the data I show you here is color coded. If it's right circular, it will be red color. If the left circular, it will be blue color. And the first question is one addressing actually can we see photoluminescence? The second is how does it connect to magnetizations? And initially, what my student did is, he just shone light to a monolayer, and he indeed see a luminescence. But the data is taken at the 70 Kelvin, which is above the Curie temperature. There's another story in these measurements you can see is that the luminescence actually come out the 1.1 eV. So 1.1 eV is very close to the silicon gap. So the sample we have is all at the silicon, right, the time, right? And it's very difficult to distinguish the signal is from the sample or from the substrate. At least my student convinced me to buy a nice detector for him, which is $40,000, just looking for the single peak, which is maybe there, may not be there. And it was dangerous because it's already his 4th year, If he failed, he's going to be punished. But luckily, right, it worked. So later on, once we realized there's a real signal, what they did is now we make sample actually on sapphire because the sapphire doesn't have a gap at the 1.1 eV. Okay. The other thing I want to point to you is you can see the intensity actually extremely weak. It's only like 0.4 cuts per microwatt per second. It's about at least 2 to 3 order of magnitude smaller than these, for example, transition metal dicotonates. Okay, extremely weak. So you have to be very patient when you're taking this data. Then next, what we did is just cool down the sample to 15 Kelvin. Again, right? We don't apply any magnetic field. Okay, there's no magnetic field applied in the whole process. Now you see, well, there's a spontaneous circular polarization in the system. Right? This PO shows it's circular polarized. This demonstrates that indeed a ferromagnetic order spontaneously formed, and it's out of plane. Right? Out of plane is important because in plane, right, the light circular, with angular momentum going out of plane. If the magnetization is in plane, actually, you're also not going to see these circular polarizations. So this is a kind of independent measurement of magnetic order. Okay. Then the next thing we do is want to prove it is indeed coming from magnetic order. Then we measure the luminescence as function of magnetic field. And the top is starting from 0 Tesla. Then we increase the magnetic field and actually flip the magnetization to the up directions. You can see the polarization is flipped, right? The red now is stronger than blue. Then we can go back to 0 Tesla because of hysteresis, right? The memory effect. Then the polarization is still radically stronger. Then again, until I apply a large enough negative field to flip the polarizations, now the circular polarization also flipped. Okay, so we can plot the degree of polarization as function of a magnetic field, and we see this hysteresis curve here. So this hysteresis curve I show you here is very different from a MOKE I just told you, right? MOKE is measure actually the light scattering from the sample at the same frequency. But what I measure here is luminescence, which is light emitted from the sample itself. but both shows these hysteresis coming from, they point to the same origin of the signal, which is the ferromagnetic order. Okay. The other thing we did is we can look at the luminescence from bilayer, right? At the large negative field, we see circular polarizations, where in the anti-ferromagnetic state, right, net magnetization equals 0. Now you can see the spontaneous circular polarization actually vanishes. Then we can apply a positive field, right, to polarize the systems. Now the spontaneous polarization comes back. All right. And then I can plot the degree of polarization as function of magnetic field in this plot, right? It looks very similar to the MOKE, so everything is consistent. The last thing I want to mention to you is that I told you that the signal is very, very small. This is because the transition I'm looking at here, actually, it's a molecular orbital transitions. So the other is it's happened between, in this chromium atom, which is a 3D ions. So therefore, we measure actually D to D transition, which is symmetry forbidden, because there's no change of angular momentum, right? But the reason we can see that because the crystal itself, you look at the unit cells. It's a chromium atom in the center, then with 6 outlay on the corner. It's octahedral edge sharing structures. So if you're familiar with chemistry, at that time actually I don't, So I have to talk to my chemist colleague. He said, "Well, this is the common, right? It's just a Ligand field." At that time, actually, I never heard of what Ligand field is. So now I know, right? For octahedral symmetry, and especially with transition metal structure like that, all the electronic transition is considered as a molecular orbital transition, highly localized. Okay. But what it means is that the transition happens inside of these unit cells. Then because it's a Ligand field for chromium has 3D orbitals, the physical property is determined by the orientation of this orbital I show you here. For example, there's 5 of them. I show dxy, dxc, dy. If you study group theory, you will know what I'm talking about, right? All these angles is important. And there's another 2, which is symmetric, is this one. So it depends on the angle of these orbitals, then they can talk differently to these outer items. Right? Then there will be different mixtures to these orbitals. So I won't go into all the details of that, but the short summary is for the transitions we care about actually is from these 3. The ground state is A24. Then there's a T24 and a T14. So the A and the T is represent the irreducible representations, the group basically. Here what I show you is the reflection measurements from the samples, and you can see there's about 4 peaks. The lowest energy one is coming from the transition I show you here, from A24 to T24. Then there's another one, what I show you here is from A24 to T14. Both of them is coming from these D to D transitions. The reason, as just mentioned to you, right, D to D transition is actually symmetry forbidden. But the reason we can see this D to D transition here, because first of all, there's anisotropic phonons. So anisotropic phonons actually can break the local symmetries. The second is in these, I'm going to show you a little later, is so if you from the top, you look at the top of the crystal structure, there's a 6 chromium atom next, from a hexagonal lattice structure. So between chromium and chromium, actually there's exchange field. So this exchange field is anisotropic. It can also break the inversion symmetry in these octahedral unit cells. And the last is for this transition metal, if you have these octahedral unit cells, there's a famous kind of empirical rule is the Young-Taylor distortion come into play. So all these 3 factors can break these local inversion symmetries. Then once if you broke the inversion symmetries, then this D to D transition will become symmetry a lot, but still very weak. Then there's the other 2 peaks at the high energy side here, what I show you. So these coming from the Ligand field transition. What it means is from the transition between the chromium d orbitals to the p orbitals from this iodide. Okay, so these kind of charge transfer transitions. Then the luminescence, what I show here, is coming from 1.1 eV, right? It's also from the lowest ground states, but there's a huge energy difference between the absorption to these luminescence. So this difference coming basically shows there's an extremely strong electron-phonon interaction resistance. So this shift is coming from these. Basically, it's a measure of the Hwang rays strength, the electron-phonon interactions. Yes.
Did you try to add an electric field to explicitly break the inversion symmetry to see whether the signal gets amplified or not?
Yeah, I think we did that. I don't think we see strong effects there. So the reason is I think this electric field actually, you can break inversion symmetry, but it's just too weak compared to the internal field.
Mm-hmm.
Yeah,
Mm-hmm.
it's just too weak. Okay. So far I covered the fundamental property. Now I'm gonna take a step forward and look at some effects we can do with these layered antiferromagnets. So the first example is right. This chromium trilayer is a layered antiferromagnetic insulator, and we can go very thin. In 2D materials, there's a very famous a kind of a wonder insulator, which is hexagonal boron nitride. Using hexagonal boron nitride, we can create devices with really high qualities to access the physics you cannot do with low quality devices, for example. Or you can use a hexagonal boron nitride as a tunnel barrier to make tunneling down. Then in our case, chromium trilayer I consider is a solid like boron nitride, probably not as good as a substrate, but has a magnetic functionality, right? So we can use that to observe new features. Okay, so the example I'm going to tell you is this giant tunneling magnetoresistance with the spin filter effect. So what that means is we know this GMR effect, right? In the traditional GMR, you have two ferromagnetic contacts and with a tunnel barrier, which is non-magnetic. So it depends on the relative orientations from these two ferromagnetic contacts. They can be parallel or anti-parallel, right? Then from there, we get this ratio of this resistance, then we get a tunneling magnetoresistance TMR. So usually the tunnel barrier is critical for the TMR, and for state-of-the-art, if they use MGOs, and then you can match the momentum, the scattering momentum, etc. of the MGO by pick particular 3D magnets. So the state-of-the-art for this TMR, for this particular system, is on the order 500 at room temperature and about 1300 at low temperature. Okay. Then there's another scheme. It's called spin filter TMR. So for this scheme, the difference is now the contact becomes non-magnetic, but the tunnel barrier is magnetic. Okay. In particular, for this tunnel barrier, imagine you have two spin filters. So you can switch the system from these two spin filters aligned with each other or anti-aligned with each other. Then in this case, we can also realize tunneling magnetoresistance, right? But the challenge is, how can we get a material, how can we get a magnet with these type of spin filter functions? Basically switch from aligned and anti-aligned configurations. So about 10 years ago, right, the group at the MIT from Lateral group, they engineered these artificial spin filters with europium sulfide and with aluminum oxide and another europium sulfide. The reason they put aluminum oxide is, first of all, they don't want these two europium sulfide to talk to each other. Otherwise, you cannot distinguish the property of these two europium sulfide, right? The second is that they grow different thickness of these europium sulfide. Then they have a slightly different cohesive field. Then you can treat them as different spin filters. With that, you can obtain these spin filter tunneling effect and with this TMR on about 30% at the low temperature. Okay. So the drawback of these type of systems is you can see, first of all, it's complex structures, and the second is it's actually thick. So for studying any tunneling behavior, we know the tunnel barrier need to be thin, right? Otherwise, the tunneling is not going to work. It's not a quantum mechanic tunneling anymore. And it turns out the bilayer chromium trilayer I just talked to you is a perfect spin filters, right? The spin ground state is exactly at two spin filters, but anti-aligned with each other, right? It's interlayer antiferromagnetic coupled. Therefore, if you pass current through the systems, it will be suppressed. Then we can also apply magnetic field to align two spin filters in the same directions. Then the tunneling current will be increased. We can also align the spin filter in horizontal direction, for example. So this is basically the bilayer CI3 is a kind of perfect system to realize these spin filter effects. Here's a device image. We have a graphene on top and bottom as a context, and we have a bilayer Ci3 in the middle as a tunnel barriers. Here's just an optical image of the device. And the first we measure the tunneling current as function apply the bias at 0 Tesla. Then I can increase the magnetic field to align the spin in the vertical direction. Now you can see the red curve, right? The current is stronger than the purple one. You can also align the spin in the horizontal directions. The tunneling current is even a little stronger. So the difference between these, the spin align out of plane and in plane is coming from, it shows basically as an anisotropic magnetoresistance in the system. So we can define these tunneling magnetoresistance, follow these definitions. And we found is for bilayer, we can already get these TMR on the order of several hundred, right? From 400 to 500%. So these are already much larger than the European sulfide system you can get and close to the state-of-the-art of MGO systems. So we can confirm the phenomena we see is coming from these spin filter effects. So top curve, the top panel I showed you here, just a second. The top panel is the Kerr rotation measurements, give us the magnetic states. The bottom is the same device. We do tunneling measurements. So you can see, right, the tunneling measurements at the low field is the tunneling current is suppressed corresponding to these anti-ferromagnetic ground states. And when the magnetic field is large, right, all the spin is aligned, the tunneling current becomes large. So these sharp transition, it's a spin flip transitions as we see in these MOKE measurements. So everything is consistent. And we can extend this idea into a little bit more complicated systems. Right? I'm going to ignore these slides. This basically shows we can apply in-plane magnetic field and to see these spin canting effects and to measure these anisotropic field, which is about 3.8 Tesla. So we can further increase the TMR by increase the layer number. So this is what's nice about spin filter concept, because then you can artificially create, add functions to these spin filter in the middle, right? So if you go to trilayer, now you will see in the trilayer you have two interfaces compared to the one interface in these bilayers. Therefore, you already imagine, right, the tunneling magnetoresistance will be increased. So this is exactly what we see for the trilayer. Okay, we have this co-rotation map, and with these tunneling current measurements, we do observe this TMR increase to about 3,000%. And we can keep doing that, go to 4 layers, for example, then the interface for this anti-ferromagnetic coupling increases, then the TMR can go as large as 20,000. And as other group shows, you can keep increasing it. You can go to even million%. But what I want to show you here is in the 4 layer, in the tunneling measurements, we see a plateau showed up. So this intermediate state is corresponding to the intermediate, magnetization state I showed in the MOKE measurements, right? So this is nice. The reason is, well, because if we think about each step corresponding to 1 bit, then there's a potential to realize multi-bit storage, right? Imagine, in the magnetization system, what we do now is you have a spin up, spin down, so it's a 0 and a 1. But it's possible you can engineer multiple states, then we can increase the storage capacity. Not just 0, not just 1. You can have 0, 1, 2, 3, 4, for example. It depends on the layer configuration we're going to put in there. Okay. All right. I'm going to go back to this a little bit later. But the key message is, well, there's M equal 2 states here. These M equal 2 states corresponding to these intermediate plateaus. I'm going to show you how we can do some kind of a manipulation on this particular state. All right, so now I'm going to go to what I told you. The first part is you can already find it we published, and in the last part I'm going to show you some new results. One is going to actually show up today in Nature, and the other one hopefully we're going to come out soon. Okay, so there's actually a mystery in this interlayer antiferromagnetism, right? I told you, I was puzzled at the beginning by these interlayer antiferromagnetic couplings. The reason I was puzzled because before our work, there are already theoretical calculations on these particular crystals, and what they show is the crystal Ci3 itself should be ferromagnetic from bulk crystal all the way to monolayers. But clearly, my experiment shows actually the atomic thin limit is anti-ferromagnetic couple, right? So what's going on there? And also my collaborator, his bulk crystal measurement also shows it's a ferromagnetic. And in the last couple of years, there's quite a bit theory work. And in this theoretical work, what they show is, you see these keywords, right? Stacking. And they also another work shows, basically in the supplementary, they also discuss the stacking, the impact of stacking on the magnetic orders. So here, just summarize the key concept is, for these crystals, the calculation shows there could be two stable stacking order. One is rhombohedral, it's called AB. The other is monoclinic, AB prime. Then for these two different stacking order, for the rhombohedral, we'll get the ferromagnetic order. But for the monoclinic stacking, actually we'll get the anti-ferromagnetic interlayer couplings. Now then the question is, well, what the stacking order it is, right? So for the bulk crystal, my collaborator already measured. There's actually a crystal structure phase transition at the around 200 kelvins. So the high temperature is a monoclinic phase. When you go to low temperature, it's a rhombohedral phase. Therefore, in a bulk crystal, it's ferromagnetic order, right? Consistent with the theory. If it's rhombohedral, it should be ferromagnetic. Now, well, what's going to happen in these bilayers, right? Is it the monoclinic or rhombohedrals? So to identify these, we use a second harmonic generation measurements. The key message for second harmonic is it's very sensitive to crystal symmetries, because in order to get a second harmonic generation, under these electrodipole approximations, the inversion symmetry will break. And the second harmonic generation has been used actually to measure these anti-ferromagnetic order in the bulk crystals, and there's quite a few interesting review work. If you want to know more about it, you can look into these papers. So for our work, let's just look at the crystal symmetry of these chromium triide. And in the monolayers, has these D3D crystal symmetries. Actually has an inversion symmetry, so there's no second harmonic generation. And in a bilayer, when these two crystals align in the same directions, no matter how you slide them, right? Because monolayer is already central symmetric. If you put another material, you can just convince yourself. If it's also in the same orientation, no matter how you slide them, the central symmetry doesn't break. Okay. So for the bilayer, it's also central symmetric, and the second harmonic generation is electrodipole forbidden transitions. But now if we add these spinning structure into the systems, okay, you see is in this anti-ferromagnetic ground state, right? If you do inversion symmetry operations, now the left hand state is going to go to the right hand side. These two are different state. So what it means is inversion symmetry actually breaks due to this layered anti-ferromagnetic order. Therefore, the second harmonic generation should be allowed. Now, if I apply a large enough magnetic field to turn the system into this ferromagnetic state, then the inversion symmetry actually restores. Then the second harmonic generation should be electrodipole forbidden again, right? So this work is a collaboration with the Sui Wu group at the Fudan universities, here just the setup. First, we measure the second harmonic generation from the bilayer at the 50 Kelvin, which is above the Curie temperature, and clearly we don't see any second harmonic generations. Then we cool down the samples, right, at the 15 Kelvins. So at the 5 Kelvin, actually, in this case, first we measure the second harmonic generation intensity map at the zero field, means in the anti-ferromagnetic ground state, we do see a very strong second harmonic generation signal show up. Second, if we measure the -1p, the spin aligned, now you can see the second harmonic generation actually vanishes, right? This is consistent with what I just told you. Anti-ferromagnetic states break the inversion symmetry, but the fully spin polarized states actually restore the inversion symmetries. And we can also just map the signal strength at function of temperatures. So below the Curie this critical temperature, the signal is strong, but it drops as we warm up, and until vanishes as the magnetic order also vanishes. Okay. So this demonstrates the second harmonic generation we measured is really coming from these layered anti-ferromagnetisms. And we all can quantify the strength of this second homogeneous signal. It's remarkably large. So here I compare, for example, the second homogeneous signal from this, the classic example of bulk crystal chromium-2 trioxide. It's an antiferromagnet. And the signal from this bilayer actually is about 500 times larger than these bulk crystals. We can also compare the SSG from these, the other 2D crystals, like monolayer MOS2 or monolayer HBN. The bilayer CL3 is also stronger, okay? So this gives us a kind of unique opportunity, right? We can control the magnetic order then to switch these very strong nonlinear optical signal. Okay, the next is, now we look at the crystal symmetries between, the difference between this rhombohedral and the monoclinic, right? Rhombohedral has these 3-fold rotation symmetries, but the monoclinic is C2H. What it means is you only have a 2-fold rotation symmetry and with a mirror plane. Then we can use these. We can use the angle result, the second homogenization, to kind of let me skip it to resolve the symmetry of the crystals. So here's what I mean, right? We do these azimuthal angle result second homogenerations. What I show you here is this azimuthal angle phi is in the plane. And here's two patterns you show here, right? The black color means excitation laser and also detection laser polarization. They're collinear with each other. And the red color means excitation and the detection is orthogonal to each other. It's just two different detection schemes for the second homogenerations. And you can see that the pattern actually doesn't have a 3-fold rotation symmetry, right? It's clear. So what it means is rhombohedral is now the crystal structure for this bilayer. But if you look at it, well, you clearly see there's a mirror plane here, right? And the solid line I show here is the fit of the data, use the C2H symmetry, all right? So basically, well, the bilayer actually look like a monoclinic structures. To confirm that, we can also try do the same measurements, but they use different excitation laser energies. So once you tune laser energies, the detailed pattern of the second homogenization, it changes, right? This is because, well, this detailed pattern is determined by the local electronic transition, which is in resonance with the laser. So the pattern will rotate. But for all these 3 patterns, right, you can already tell there's one thing is the same, which is this mirror plane, always in these directions. This is determined by the crystal structures. We can also fit the data really well with C2H symmetry, all these 3 samples, all these 3 different patterns. So the conclusion is, for bilayer chromium triide, it has these C2H symmetries and it has monoclinic stackings. And there's no monoclinic to rhombohedral crystal structure phase transition in Tomlin-Singh chromium triides. Okay? All right. And we can keep looking to these problems, look at the stacking order. So let me just another kind of a careful look. So for unit cell, right, there's a chromium atom in the middle. And there's 3 out at the top and 3 at the bottom. And both of them actually has these 180-degree rotations from each other, from top and bottom, okay? And if I look from the top, now you can see we label a color here, right? So there's a blue color, 6 of them here. These are the 6 chromium atoms from these hexagonal lattice structures. Then there's 3, the red 3 other atom, which is the one at the top. And the gray one is 3 at the bottom. So we can link them with these solid line triangles, right? The green solid triangle is the atom on the top, this triangle. And the bottom one, this dashed one is at the bottom, okay? Remember this picture? Then we can look at we can simplify these. Okay, now what I'm gonna do is I only draw these green ones, right? And look at here. So this is a top view simplified structure. This triangle corresponding to these green triangles. And I have 2 vectors here, which is the AB lattice. All right, this is how we define in the monolayers. Simple structure, right? 4 triangles with AB is my lattice vector, my vectors. Then if you add another layer, right, now I have a bilayer systems. So this pink color represents the top layer structure, and the green one represents the bottom layers. Now, these top and bottom, these triangles, you can have a relative shift, okay? They have the same orientation, but they can have a relative shift. So these shift to give us these called R-type stacking structures for the bilayer chromium triadides. And you know, the middle row here is the unit structure from this bilayer. You can see how these shifts happens, right? You can the bottom row just shows what is the coordinates in terms of A and the B, these two vectors. So there's a many different kinds actually. It's not that very simple. Depends on these vectors, how they shift. We can have a rhombohedral structure, we can have a monoclinic structures, for examples. And there's another type, which I haven't mentioned to you. It's called H-type stacking. The difference, right, in the R stacking, what I mentioned to you in the R stacking is the top triangle and the bottom triangle has 180-degree rotation, right? Remember? But for R stacking is for single layer, the top 3 atom, the bottom 3 outer atom, actually they orientate in the same direction. There's no 180-degree rotations, okay? So with that, you know, there's another structure which is called H-type stackings. And nobody discuss it, right? Because all the, you know, all the paper we see and all the X-ray diffraction says this crystal should be in the R stackings, but there's no H stacking. So there's another mystery. Another mystery is another class of chromium trihalide, which is chromium triboride. Somehow, right, all the paper, and including us, we also studied, chromium triboride is actually a ferromagnetic insulator. This is kind of mystery because chromium trihalide and chromium triboride, they're the same thing, right? The only difference is just the highlight is different. But in the same class, why one material is antiferromagnetic, the other is actually ferromagnetic? Now we all know, right? Has to be something to do with the stacking. So, Siwei and also Chen Wei at Fudan University, they look at these problems when we discussed, the physical difference between these two. So what they decide to do is, we all know that for all the exfoliated chromium triboride, so far for every thing we measured, also from different group reported, they're also ferromagnetic. So what they decide to do is, they actually started MBE growth. So here they show they can do MBE growth of monolayer chromium triboride, and also with bilayer islands on top, right? Then, because they do MBE growth, means they can directly use scanning tunneling microscopy to image the atomic structures. Then they can use magnetic tips, these spin pulse tips, to study the magnetic order at the same time. Then you can directly correlate the stacking order to this magnetic order, okay? That's the basic idea. So first, well, just imagine the monolayers, and they see all these triangles, okay? So these triangles, each, there's 3 atoms here. These triangles corresponding to the 3 bromide atom on top. As I taught you at the beginning, right? These triangles, okay? Do you follow me on this part? Then you can do spring porous STS or ST measurements, and then you can see this hysteresis, right? So it means it's ferromagnet in the monolayer. It's not a surprise. Well, then we can also look at the bilayers. Now this is what's interesting what's the interesting result. So in the bilayer, you can image the atomic structure of the top of the bilayer. Okay, then you know what's the orientation of this triangle, right? By imaging the top, you know the triangle orientations. Now you can also image the bottom layer, which is the extended monolayer underneath this bilayer, right? We extend out. So then you can map out the triangles of this bottom layer. So basically now you know the crystal structure, this triangle orientation in the top layer. And now also you also know the triangle orientation in the bottom layer. Make sense, right? Then you can put them together. What we found is actually it's H stacking. It's not the monoclinic rhombohedral R stacking I was talking about. So it's H stacking. So for the H stacking, indeed you have a ferromagnetism. That's what the conclusion, okay? But what's really interesting is they also found there's R stacking in assistance, just random. So it's the same idea, right? You just measure the crystal structure, basically the orientation of these triangles for the top layer and the bottom layer, then you extend it, you figure out what's the stacking order for these bilayer, then it turns out to be R stacking. And in the R stacking, it determines actually it's anti-ferromagnetic, right? So these are actually really nice results because we directly correlate these stacking arrangement to the magnetic orders. Okay, so now hopefully we establish there's a correlation between the layer stacking arrangement, right, to these magnetic orders. And last, I want to show you examples how we can control this layer stacking and to these magnetic orders. So let's go back to chromium triode, and I remind you the simple results we have. Let's see how much time I have. Maybe another 10 minutes, right?
Yeah.
Yeah, that's perfect. So for this, remember it's monoclinic, it's antiferromagnetic, and for rhombohedral, it's ferromagnetic. Then we try to apply the hydrostatic pressures, okay, to control the interlayer couplings. So here's examples, right? What we have is we make these sample with, basically tunneling structures I just talked to you. And we measure the tunneling current, okay, at 0 pressures. Then we can increase the pressure. Just skip these slides. You can increase the pressure, you can see the critical field for spin flip transition increases, right? This just shows by applying pressure, you indeed increase the interlayer couplings, okay? And I can map out the interlayer coupling as function pressure, represent these black dots. We can increase the interlayer coupling actually by twice, factor 2. The blue one represents the critical temperature for magnetic order to form, but you can see the critical temperature doesn't increase much, only increase from 44 Kelvin to about 47 Kelvin. This is small. And this also makes sense because the critical temperature actually determined by intralayer exchange interactions, but the intralayer exchange interaction doesn't really depend on interlayer coupling, right? So all the results make sense. As we keep increasing the pressure, what we see is this sharp spin flip transition actually vanishes at the highest pressures. What we see is only this kind of slope, magnetoresistance. This is coming from the graphene contact, okay? But the spin flip transition have disappeared. What this indicates is, well, maybe the antiferromagnetic states already transition into a ferromagnetic states, right? To confirm that, we take the sample out, then we perform magneto-optical co-rotation measurements. And here, just to remind you, if for a pre-Stein bilayer in the monoclinic structure, we do see the vanish of these co-rotation signal. So we do have antiferromagnetism. Now for the sample after we apply pressure, okay, the co-rotation signal is complete change, right? Now we see a strong hysteresis curve. Bilayer now becomes a ferromagnet after the pressures. So the simple message is this layer sliding actually tune the system from these antiferromagnetic to ferromagnetic transitions. So what's interesting is, well, in the trilayer, we can engineer actually multiple magnetic states. So again, right, in the trilayer, the top one is the tunneling current measurement without pressure, the bottom is with pressure. And we can see the critical field for spin flip transition increases just as we saw in a bilayer, right? Everything is consistent. But what's interesting is at the higher pressures, I observe there's intermediate states showed up, okay? This means there's new magnetic states appeared at the higher pressures. And this new state is coming from another antiferromagnetic state. So here, I define two types of antiferromagnetic states. The first one is called antiferromagnetic states 1 or F1. F1 is just the one I already talked to you, right? With two antiferromagnetic interface. Spin up, spin down, spin up. So there's two interfaces, it's antiferromagnetic, just like natural crystals. But for antiferromagnetic state 2 is AF2. Now there's only one interface is ferromagnetic. The other interface becomes ferromagnetic. So what you can think of is, if it's just a bilayer, right? the system already become ferromagnetic, right? Think about the bilayer I just talked to. It's ferromagnetic. But now I just add another layer to the bottom. So it means the bottom layer, the layer sliding hasn't happened, but the top layer, there's already layer sliding. The stacking already changed. So we can confirm that is, look at this spin fluid transition. So you already know, right, as we apply the magnetic field, and when the Zeeman energy overcome the spin flip transitions, overcome this interlayer coupling, then the spin will flip. But for AFM2 only has one interface, right? And for the AFM1 has two interfaces. So what it means is the energy we need to flip the spins in this AFM1 to have to overcome these two interfaces compared to one interface in the AFM2, right? So the critical field we need to flip the spin in the AFM1 should be twice what we need for the AFM2. Okay, do you follow this? Very simple argument. So we can see there's two spin flip transition, right? The first transition happened at the 1.7 Tesla. Second is, roughly speaking, it's about twice of it. It's 3.7 Tesla. So the first spin flip transition actually pointing to this AF2, flip into these ferromagnetic states, and the second transition corresponding to these AF1, the spin flip transition, or into this fully spin polar state. Okay, and what's interesting is now we park our magnetic field, and now I scan the bias. Okay, here's what I did. We scan the bias. But we found we can use electric current to flip these two states. Okay, so first of all, I want to tell you this transition, this whole process is non-reversible. Only happen once. So it's also lucky you have a good student. He take really careful data, so he didn't miss this. Right? If you just take a bias, you don't know what's going on, then you don't know basically. So what we did is we just scan the bias, and then we see a jump. Then we scan the bias back. You got this blue curve, but doesn't go back to a red curve, right? So this transition happens where you have electric current to switch the system from these antiferromagnetic states 1 into antiferromagnetic states 2. So how do I know that? Well, very simple. Now what I do is I can scan the magnetic field again to measure tunneling current. So the top point is before the switch happened, the bottom is after the state switching. So what you see is after state switching, only the lower field transition, right, stays. The top one already vanishes. So what that means is now all the states I have is in this antiferromagnetic states 1. Sorry, in the antiferromagnetic states 2. Okay. All right, and we can also image these magnetic states in a real space. So we take the sample out and we do these co-rotation measurements. On top here, I show the optical image with 2 layers and 3 layers. But in this sample, I actually have a 2 layer there. So if I just do a MOKE measurements on these 2 layers, you see ferromagnetic states. So consistent with what I showed you. And now if I map the different spots in this trilayer, P and Q and R, we see very different behaviors. Okay. Let's see. So for these ferromagnetic states, right, at this particular spot R, we do see a ferromagnetic state show up. But in this P and Q, they have 3 spin flip transitions. And we find these 2, one is AFM, one is the other AFM2. The way to do it is very simple, as I already mentioned to you, right? Just look at the magnetic field that we need to realize this spin flip transition. For the AFM2, only one interface is antiferromagnetic. For the AFM1, there's 2 interfaces, right? Therefore, the field we need for AFM1 for this spin flip transition should be twice for AFM2. So that's what we see. For AFM1, we need 2 Tesla. For the AFM2, we only need 1 Tesla. So that's how we can tell we do have these 2 different states. Then next is we try to map these 2 states out in a real space. And the little trick we do is, you can see the spin flip transition, right? For all these fields, for all these different magnetic states, they happen in a different critical field. So the first, imagine, just follow me. I scan the magnetic fields down. I take a MOKE spatial map at the 2 Tesla. Okay, so this is the map I got. Then I switch fields down again, and I park at this particular field at 1.3 Tesla. Then I take another map, right? So what you see is, at these 2 particular fields, only AFM1 has spin flip transition. AFM2 and the ferromagnetic states, both doesn't change, right? Therefore, I just take a difference of these 2 maps, and it will give me a net signal. this net signal, it will corresponding to this antiferromagnetic states 1, right? So this area. Okay, then next, I can do the same measurements. Now I keep swing my field down. I take a map of 1 Tesla and take another map at 0.4 Tesla. And here, only the AFM2 has spin flip transitions. Then I take a difference of these two. Then I get this area corresponding to the antiferromagnetic states 2. Last, let's try to map out these ferromagnetic states. It's a little more tricky for the ferromagnetic states. Let me go back a little bit. We take a map at 0 Tesla and minus 0.5 Tesla. So for these two fields, the antiferromagnetic phase 1 doesn't change, but for FM2 also has spin flow transitions. But there's a difference, right? You can see the signal change for the ferromagnetic phase is much larger than the signal change found in this antiferromagnetic state 2. Okay, so you can see the large drop here, right? Larger than 4%. So what I do is then we can take a difference of these two maps, but set the signal threshold larger than 4%. Then we can isolate this area for these ferromagnetic states. Okay, so by doing this, we actually to map out this the area for these different magnetic phases, right? As I show you here, we have antiferromagnetic states 1 and antiferromagnetic states 2, and with ferromagnetic states. So this is just a simple example. We can control the pressure, control different layer stackings, then control these magnetic configurations in the system. And lastly, the example I want to show you is, well, this process is actually a little bit random right now. We cannot control it. For example, here's another sample we measured where it has 2 layers, 3 layers, 5 layers, and we just apply pressure, then we take it out from the pressure cell, we do MOKE measurements. This is just a 3 particular spot I choose. So you see it's all we see is a hysteresis curve. So it means, actually in this particular case, we turn the whole sample into ferromagnetic states. Okay. All right, so I was just stop here, and for the first part, yeah, welcome. Yeah, any questions? Yes, please.
So in different layers of samples, when you switch the ferromagnetic and the antiferromagnetic states, they have like different size of hysteresis. Is it related to the number of interfaces, or it's related to other?
It's related to the anisotropies.
Anisotropies?
Yeah.
I have one question.
Yeah.
So the pressure has the effect to cause a phase transition, let's say from Rhombohedral to Monoclinic. So after you take out from the pressure cell, the state of the Monoclinic remains. So is there a possible way to further reverse back?
Yes. So this is a very good question, and we're working on this. Is the simple solution just heat it up, right? Heat the crystal up to some temperature, then the phase transition should happen again. The crystal structure.
Yeah. Then what is the phase transition temperature?
We don't know.
I see.
That's a work in progress. Yeah. Because imagine, right? All this measurement talking about is irreversible, and there's chance you heat it up to someplace damaged. So it's not a fast turnaround measurements. Yeah.
Have you tried to rotate the sample to switch from one stacking to the other?
Yeah, we did that. And this is also hard to control because of when you stack them, right? There's a lot of the angle rotations, and also inhomogeneous in the samples. We see all kinds of states actually. So it's difficult to resolve.
Any other question? If not, let's thank our speaker again.